Alright, so this is the first of two videos for logarithms. This is coming off of the exponential video and the inverse functions video. So in the inverse video, what we said was that if you have a one-to-one function, then f has an inverse. The importance of being one-to-one is sort of that you pass the horizontal line test is the nicest way to say it, but anytime you take two different inputs, you have to get two different outputs, which is another way of saying it. Remember that inverses work by switching the x and the y values. So for example, if you have 2, 3 on f of x, then you have 3, 2 on f inverse of x. And this is important if we're working with the function f of x, and I tell you that 2, 3 is on f of x, what that means is that f of 2 is 3, because when you plug in 2, you should get f of 2. And so that's over here, f of 2 is 3. Likewise, when we take f inverse of x and we get 3, 2, 3, when we plug it into f inverse, should give us 2. Right? The y value is always the function applied to the x value. So f inverse of 3 is 2, f of 2 is 3. And so you can see how an inverse relates the output to the input based on the original function. So if f inverse is the inverse for f of x, then we get two things happen immediately and totally for free. f inverse of f of x has to be x, and f of f inverse of x has to be x. So a function and its inverse always undo each other. So if you plug x into f, and then take that and plug it into f inverse, you get x back. If you take x and plug it into f inverse, and then plug it into f, you get x back. And this works for any value of x, which makes sense. So it's important, if x isn't in the domain of f, the first one won't make sense, this won't make sense, right? Because f of x won't make sense. And more importantly, if x is not in the range of f, then it's not in the domain of f inverse. And so that won't make sense. Okay, so now we're going to actually get on to the point of the video. We have this fact that whenever we take any positive non-one number, when we have a to the x equals a to the y, x equals y, this came from our exponential video. And what it did was it allowed us to solve equations, but it's actually way more important than that. That equation is equivalent to saying that a to the x is 1-to-1. And therefore, a to the x has an inverse. Right? And you remember our graph of a to the x, it looks something like this. Right? And you can see that any horizontal line is going to hit at most once, which is saying again that our function is 1-to-1. And so a to the x has an inverse. We call the inverse log base a of x. Right? This is log base a of x. That's how you read this. So this a refers to the base, and it's directly related to this a. So I have starred this double-sided arrow. Log base a of x is y, if and only if a to the y is x. The way you think of this if and only if is equals as expressions. So if you ever have the left side, which is log a of x equals y, you can replace it with a to the y equals x. And so we now have a way of dealing with the symbol log a of x. So a couple of things for free. Remember, if we go back here, in the red boxes, f inverse of f of x is x, and f of f inverse of x is x. And so if you use f of x equals a to the x, and f inverse of x equals log a of x, which I wrote down here, then you can get fact 1 and fact 2 by doing f of f inverse and f inverse of f. Right here is f of f inverse, and down here is f inverse of f. But these are pretty neat. These are two things that are just always true, and the reason they're true is because log and the exponential are totally inverses, and so they're just true. Now, going back to this, log base a of x equals y can be replaced with a to the y equals x. The way you kind of want to think about it is it's always the base to the result equals what's inside, right? Even though sort of in a very evil fashion this looks like a to the x, you'll never have a to the x when you rewrite it. So if you want to evaluate log base 2 of 8 equals y, you can replace it with 2 to the y equals 8. And this becomes an equation like we've seen before. We have 2 to the y equals 8, which equals 2 cubed, which means y equals 3. Log base 4 of 1/4 equals y. We take that and we replace it with 4 to the y equals 1/4. And then we write 4 to the y equals 1/4 equals 4 to the negative 1, and so y equals negative 1. So that's one type of equation we can solve using just the replacement formula. So here again, I have the replacement formulas already written up. We want to solve log base x of 9 is 2. That's equivalent to saying that x squared equals 9. And so when we solve x squared equals 9, we get x equals plus or minus the square root of 9, which is plus or minus 3. Now, bases are never negative. I can't stress that enough. The base can't be negative, and so we only keep x equals 3 as our answer, and x equals negative 3 we reject. And so x equals 3 works. Log base x of 4 is 1/2 if and only if x to the half equals 4. So we're going to solve the left side by replacing it with the right. The way you get rid of the half power is by squaring both sides. And on the left we get x, and on the right we get 16. And so log base 16 of 4 is 1/2. Now there's one last place we can put variables, and so we get log base 2 of x equals 3 is equivalent to 2 cubed equals x. Well, that's just x equals 8. And log base 5 of x equals 1/3, if and only if x equals 5 to the third, that's just x is the cube root of 5. And so you can see these are sort of the most boring possible logs to solve, because they're sort of so easy. So here's a couple of properties of log, and these work for any base. And since they work for any base, what I have not done is I have not written any base down here. Whatever base you put, these are true. So these are two of the most important properties of log. Log changes multiplication inside the parentheses to the sum of two logs. Log changes division here into the subtraction of two logs. So let me just go ahead and say things which are not true. And these are that log of a plus b equals anything. I don't care. You can try to put log a plus log b. That's not true. You might try to go log a times log b. That's also not true. Basically, that the addition inside of the parentheses can't become anything nicer. And likewise, the subtraction can't become anything nicer. When you have log of an addition or log of a subtraction, generally you're stuck. Alright, so let's try to use these two properties to either combine or break up some logs. So let's do log of x times y. That's just log x plus log y. Let's do log of zw over 9. That's log of zw minus log of 9. And log of zw, since its multiplication is log of z, plus log of w minus log of 9. Now, here's another important property of log. Log takes exponents and pulls them down in front to be coefficients. And so, for example, log of x cubed is 3 log x. The log of y to the 5th is 1/5 log y. And so we can use this to really simplify lots of things. So suppose I have the log of the cube root of xy squared over z to the 4th. Right, this is a terrible expression. The first thing you can do is rewrite the cube root as a 1/3 power. Which then pulls out front. And then we have division. So we change that to subtraction. And then we change this multiplication into addition. Like that. And then all of the exponents can come out front. And so sort of one of the biggest powers of logarithm is the ability to change these complicated expressions involving powers and multiplication and division into what looks like a really simple problem involving addition and subtraction. So here's a couple more facts. Log of 1 is 0, and log a of a is 1. So let's just talk about why that's true. So if we have any base, log a of 1, that is x if and only if a to the x is 1. And the only power you can raise any base to and get 1 is 0. So x has to be 0. So that's why the left side is true. And let's talk about that. Log a of a is x is equivalent to, using our replacement rule, this is equivalent to a to the x equals a, and so x has to equal 1. And so we have two things that we can always compute sort of for free, and also this log 1 equals 0 is going to help us when we want to graph later as well. And so that's sort of it for those basic properties of log. The things that I have to emphasize for this particular video is this. This slide is the most important slide. Whenever you want to solve an equation involving logarithms, you can replace logarithms with these sort of things. And so that will make things immensely easier. I would commit this one to memory. All of these properties are really important. They allow us to do really neat tricks whenever we see complicated looking logs like that. We wind up getting totally non-complicated expressions at the end. So that's valuable. And so that's really it. Go ahead, practice the homework, get comfortable with the properties of logs so that we can do better things in the next video. Have a good day.